transformer insulation class is a critical parameter that dictates the maximum permissible operating temperature of the transformer. It is essential to select the appropriate insulation class to ensure the transformer's reliable operation and longevity. The insulation class is designated by a letter, such as A, E, B, F, H, and C, each corresponding to a specific maximum temperature that the insulation material can withstand without degradation. The maximum temperature refers to the hottest spot temperature within the transformer winding. This includes the ambient temperature, the temperature rise due to the load, and a hotspot allowance. The ambient temperature is the temperature of the surrounding air or cooling medium. The temperature rise is the increase in temperature of the winding above the ambient temperature caused by the heat generated due to the current flowing through the winding's resistance and core losses. The hotspot allowance is an additional margin added to account for localized temperature variations within the winding. These localized variations are due to non-uniform current distribution and cooling inefficiencies. The insulation class directly impacts the transformer's ability to handle heat. A higher insulation class indicates that the transformer can operate at a higher temperature without compromising the insulation's integrity. Selecting the correct insulation class is vital for several reasons. Firstly, it prevents premature insulation failure. Operating a transformer beyond its insulation class temperature limit will accelerate the degradation of the insulation material, leading to reduced lifespan and potential failure. Secondly, it ensures reliable operation. Maintaining the temperature within the permissible limits ensures that the transformer operates efficiently and reliably, minimizing the risk of breakdowns and downtime. Thirdly, it complies with safety standards. Using the appropriate insulation class ensures compliance with the relevant safety standards and regulations, minimizing the risk of fire hazards and electrical accidents. The most common insulation classes encountered in transformers are Class A, Class E, Class B, Class F, Class H, and Class C. Each class has a defined maximum operating temperature. Class A has a maximum operating temperature of 105 degrees Celsius. This class is typically used in older or less demanding applications. Class E has a maximum operating temperature of 120 degrees Celsius. It offers a slightly higher temperature rating than Class A. Class B has a maximum operating temperature of 130 degrees Celsius. It is suitable for moderate temperature rise applications. Class F has a maximum operating temperature of 155 degrees Celsius. This is a common insulation class for many general-purpose transformers. Class H has a maximum operating temperature of 180 degrees Celsius. It is used for high temperature rise applications. Class E has a maximum operating temperature of over 220 degrees Celsius. This is reserved for specialized high temperature applications. When selecting the insulation class, it is crucial to consider the ambient temperature and the expected temperature rise of the transformer. The temperature rise is dependent on the transformer's loading and cooling method. Tri-type transformers rely on air convection for cooling, while oil-filled transformers use oil as a coolant. The temperature rise is usually specified by the manufacturer, and it is essential to ensure that the sum of the ambient temperature and temperature rise does not exceed the maximum operating temperature of the insulation class. To determine the appropriate insulation class, firstly determine the maximum ambient temperature in the location where the transformer will be installed. Secondly, determine the maximum allowable temperature rise for the transformer based on the application's requirements. Thirdly, add the maximum ambient temperature and the maximum allowable temperature rise. This sum is the maximum operating temperature that the insulation class must be able to withstand. Fourthly, select the insulation class that has a maximum operating temperature equal to or greater than the sum calculated in a previous step. The question specifies two 3000 kV amps, 12 kV over 415 volts tri-type transformers for parallel connection. The specification requires a temperature rise of 65 degrees Celsius. The contractor proposed transformers with insulation class F, or 155 degrees Celsius. Is this insulation class compliant with the specification, and if not, what insulation class is required? The proposed transformer's insulation class F does not comply with the specification requirement of a temperature rise of 65 degrees Celsius. The insulation class of a transformer indicates its maximum permissible temperature. For a 65 degrees Celsius temperature rise requirement, a transformer with an insulation class H or higher is needed. Class H is 180 degrees Celsius. The F insulation class, 155 degrees Celsius, is appropriate for transformers with a temperature rise of 105 degrees Celsius, which is higher than the specified requirement. The question specified as 65 degrees Celsius temperature rise, and the insulation class F would allow for 105 degrees Celsius. To meet the specification, a transformer with an insulation class H is required. This insulation class allows for a maximum temperature rise of 85 degrees Celsius above the ambient temperature, which would result in a 65 degrees Celsius rise under operating conditions, assuming the ambient temperature is 20 degrees Celsius. Request the contractor to provide transformers with an insulation class H to ensure compliance with the specification. It is crucial to remember that the insulation class represents the maximum temperature the transformer can withstand without degradation. Operating a transformer continuously at its maximum temperature will shorten its lifespan. Therefore, it is advisable to select an insulation class that provides a comfortable margin above the expected operating temperature. Consider other factors when selecting a transformer, such as the ambient temperature, altitude, and humidity. High ambient temperatures can reduce the transformer's capacity, while high altitudes can affect cooling efficiency. High humidity can also affect the insulation's performance. It is recommended to consult with a qualified electrical engineer to determine the appropriate insulation class for the specific application. The engineer can consider all relevant factors and provide expert guidance on selecting the right transformer for the job. For dry-type transformers, the cooling method also plays a role in determining the temperature rise. The two common cooling methods are self-cooled, designated as AN or air natural, and forced air-cooled, designated as AF or air forced. Self-cooled transformers rely on natural convection for cooling, while forced air-cooled transformers use fans to circulate air. Forced air cooling can increase the transformer's capacity and reduce the temperature rise, but it also requires additional power and maintenance. The temperature rise is an important factor in determining the overall efficiency of the transformer. A lower temperature rise indicates that less energy is being lost as heat, resulting in higher efficiency. Transformers with higher insulation classes often have lower temperature rises, leading to improved efficiency and reduced operating costs. The selection of insulation class should also consider the load profile of the transformer. If the transformer is subjected to frequent overloads or short circuits, it is advisable to select a higher insulation class to provide additional thermal capacity and prevent premature failure. Short circuits generate very high currents that lead to rapid heating of the transformer windings. The higher insulation class can withstand these transient high temperatures without significant degradation. The National Electrical Code, (ONEC), provides guidelines for the installation and operation of transformers. NEC Section 450 covers the requirements for transformer protection, including overcurrent protection and grounding. It is essential to comply with the NEC requirements to ensure the safe and reliable operation of the transformer. Overcurrent protection devices, such as fuses or circuit breakers, are used to protect the transformer from overloads and short circuits. The size of the overcurrent protection device should be selected based on the transformer's rated current and the applicable NEC requirements. Grounding is another important aspect of transformer protection. Grounding provides a low impedance path for fault currents, which helps to prevent electrical shock hazards and equipment damage. The NEC specifies the grounding requirements for transformers, including the size and type of grounding conductors. Transformer manufacturers provide detailed information on the transformer's technical specifications, including the insulation class, temperature rise, and cooling method. This information can be found on the transformer's nameplate or in the manufacturer's documentation. Review this information carefully before selecting and installing a transformer. In summary, selecting the correct transformer installation class is critical for ensuring reliable operation, preventing premature failure, and complying with safety standards. Consider the ambient temperature, temperature rise, load profile, and cooling method when selecting the installation class. Consult with a qualified electrical engineer for guidance on selecting the right transformer for the specific application. Always comply with the NEC requirements for transformer protection and grounding. By following these guidelines, you can ensure the safe and efficient operation of your transformers. The efficiency of a transformer is also affected by the core material used in its construction. The core material is typically made of laminated silicon steel, which reduces eddy current losses. Eddy currents are circulating currents that are induced in the core material by the alternating magnetic field. These currents generate heat, which reduces the transformer's efficiency. The use of laminated silicon steel minimizes eddy current losses by increasing the resistance of the core material to these circulating currents. The thickness of the laminations and the type of silicon steel used also affect the eddy current losses. Thinner laminations and higher grades of silicon steel result in lower eddy current losses and higher efficiency. Transformer manufacturers often specify the core loss and no-load loss of their transformers. Core loss is the power loss in the core material due to hysteresis and eddy currents. No-load loss is the power loss when the transformer is energized but not supplying any load. These losses are important factors to consider when evaluating the overall efficiency of a transformer. The impedance of a transformer is another important parameter that affects its performance. The impedance is the opposition to the flow of alternating current. It is expressed as a percentage of the transformer's rated kilovolt amps. The impedance of a transformer affects its ability to withstand short circuits and overloads. A higher impedance transformer will limit the fault current during a short circuit, but it will also have a higher voltage drop under load. A lower impedance transformer will have a lower voltage drop under load, but it will also allow a higher fault current during a short circuit. The selection of the transformer's impedance should be based on the specific application requirements and the available fault current at the installation location. The voltage regulation of a transformer is the change in voltage from no load to full load. It is expressed as a percentage of the no-load voltage. Voltage regulation is an important factor to consider when selecting a transformer for applications where voltage stability is critical. A transformer with good voltage regulation will maintain a stable voltage even under varying load conditions. The type of transformer winding connection also affects its performance. The two most common winding connections are delta and Y. Delta-connected windings provide a higher voltage and lower current, while Y-connected windings provide a lower voltage and higher current. The choice of winding connection depends on the specific application requirements and the available voltage levels. Delta-Y transformers are commonly used in distribution systems to step down the voltage from a high-voltage transmission line to a lower-voltage distribution line. Y-delta transformers are commonly used in industrial applications to step up the voltage from a lower voltage supply to a higher voltage motor. The harmonic content of the load current can also affect the performance of a transformer. Harmonics are sinusoidal waveforms that are multiples of the fundamental frequency. Harmonic currents can cause overheating of the transformer windings and core, which can reduce its lifespan. Transformers that are subjected to high harmonic load should be derated to prevent overheating. Derating involves reducing the transformer's rated kilovolt amps to compensate for the effects of the harmonic currents. Harmonic filters can also be used to reduce the harmonic content of the load current. These filters are designed to block or attenuate specific harmonic frequencies, which reduces the stress on the transformer. Regular maintenance is essential for ensuring the reliable operation of transformers. Maintenance activities include inspecting the transformer for damage, cleaning the windings and core, testing the insulation resistance, and checking the oil level. Oil-filled transformers require periodic oil sampling and analysis to ensure that the oil is in good condition. The oil acts as a coolant and an insulator, and its properties can degrade over time due to contamination and oxidation. Regular oil sampling and analysis can identify potential problems before they lead to failure. Dry-type transformers also require periodic cleaning to remove dust and dirt from the windings and core. Dust and dirt can reduce the transformer's cooling efficiency and lead to overheating. The frequency of maintenance should be based on the transformer's operating conditions and the manufacturer's recommendations. A well-maintained transformer will have a longer lifespan and will operate more reliably. In addition to the above considerations, the energy efficiency of transformers is becoming increasingly important. Energy-efficient transformers can save significant amounts of energy over their lifespan, which reduces operating costs and environmental impact. Energy-efficient transformers are designed to minimize core losses and copper losses. Core losses are reduced by using high-grade silicon steel and optimizing the core design. Copper losses are reduced by using larger conductors and minimizing the winding resistance. Energy-efficient transformers typically have higher initial costs, but the energy savings over their lifespan can more than offset the higher cost. Several standards and regulations promote the use of energy-efficient transformers. The Department of Energy, or DOE, has established minimum energy efficiency standards for distribution transformers. These standards require manufacturers to produce transformers that meet specific energy efficiency levels. The National Electrical Manufacturers Association, or NEMA, also has a premium efficiency transformer program. Transformers that meet the NEMA premium efficiency standards are identified with a special label. When selecting a transformer, consider its energy efficiency rating and choose a transformer that meets the applicable standards and regulations. In conclusion, selecting the right transformer requires careful consideration of several factors, including the insulation class, temperature rise, cooling method, impedance, voltage regulation, winding connection, harmonic content, and energy efficiency. Consult with a qualified electrical engineer for guidance on selecting the right transformer for the specific application. Regular maintenance is essential for ensuring the reliable operation and long lifespan of transformers. By following these guidelines, you can ensure that your transformers operate safely and efficiently.